All right, today's lesson is a thing called tangents. Have you ever heard anybody use the word tangent before? Like, how do they use it? Yeah, you go off on a tangent, right? You ever hear anybody say that? That means it's kind of. I probably have. It's what students don't usually say that, but like adults might say that. It's like you're talking about one topic, but you go off in another direction, right? Completely opposite from what topic you want to help them out. So this kind of has to do with that whole phrase, a tangent. So let's draw a circle, just like we've been doing. Let me go to the circle thing. Now, we did talk about this first word, even though it's kind of weird that they put this in here because they don't really define it. They just say what the word is. And but we kind of talked about it yesterday. Do you remember we did this? We had a circle, and then we had a line that went through the circle. Remember, we had like a postulate that said, if you have a line that goes through this circle like this, then it breaks off a segment or a chord or something like that. Well, this right here is not really bisecting anything. It just goes through it, and you can get a chord out of it, right? You can get, so like if this is A and this is B, that A is a little too far away, but that's that point right there. That's that point right there. I could say it's line AB, and line AB makes a chord AB, correct? Right, that would be a line segment, right? So from A to B. But the line itself has a special name. Now, we're really not doing anything with a lot of stuff going on. What's going on? This line right here, okay, has a special name. When you have a line that goes through a circle like this and it hits 2 points on the circle, it could go through the diameter. It doesn't make any difference, okay? But if you have a line, remember, the line keeps on going in both directions, and it hits 2 points on the circle. We give that a special name. We call it a secant, S-E-C-A-N-T. It's probably a word that you have not heard before. Later on, in fact, I don't know if we'll do it in this class, but I think, depends on how fast we get this chapter finished. We may skip to the very last chapter because that's trigonometry. We've talked about that before. Yes, I definitely want to give you an introduction, at least, to trigonometry. I think it's very important because you're going to have it in Algebra 2. Well, you better have it in Algebra 2, okay? You should have it in Algebra 2. And I want you to be prepared for it. So I want you, when you take, whoever's your Algebra 2 teacher, when you get to the trig stuff, you're going to say, oh, yeah, I remember doing that in Mr. Hammer's class, okay? If that's all you remember, that's fine with me. At least you remember doing some of that stuff, all right? And some of it will come back to your memory, okay? I promise you it will. Anyway, we use a word called secant when we do trigonometry. It's really not the same as this. We also use the word, what would I say the lesson was? Tangent. We're also going to talk about a tangent. Specifically today, let's talk about a tangent. Let's put this in a different color. And it is a line, all right? But it doesn't hit the circle at 2 points. What's the only other way a line could hit the circle?
Hit the edge.
At 1 point. Okay, you could say the edge. Okay, that'd be an okay way to say it. But you could hit the circle just at 1 point. All right, so if I had a line, and where would I wouldn't take it here because that would be a what?
2 points.
That would be 2 points, so that would be a what? Word.
Secant.
Give me the word. It'd be a secant, right. I can't go like this because then it doesn't what?
Intersect.
Doesn't touch any points, right, okay? So the only other option is if, just a second, Sam. Let me draw this. Boom, right there. That's pretty good, isn't it? Why is it still white? I thought it changed the color. Is that all right? Okay. What's your question?
So what's the difference between a secant and a chord?
A secant is a line. Okay. A chord is a line segment. All right. So let's write that up here. Let's go back to white. So watch. A line segment. What's a line segment look like when we put the symbol for it? Just a straight line, no arrows. So this would be the chord. Everybody see that? So from here to here, let me watch. So from here to here, you can kind of see it yellow right there. Okay. Yeah, that would be the chord. The whole thing would be the secant. Everybody got it? You guys all done? Okay. What is this thing right here, though? This is a tangent. Okay. Why is it a tangent? Because it hits the circle just at one point. So it just glances it, okay? That's it. Just hits at one point. Now, if I blew this up, watch. If I blew this up, it looks like it hits the white circle like here, all the way to there, doesn't it? Okay, but this stuff that we use and we draw, it has width. But remember, the circle doesn't have any width. A line doesn't have any width, okay? So you can technically hit it at just one point. But when I draw it, it looks like it hits at multiple places, doesn't it? But it really doesn't. So we just have to understand that it just hits at one point, okay? Everybody good? So that's the definition of a tangent. So we're going to use that quite a bit. Let's talk about, let's just do this. Okay, that point right there where it hits, we have a special name for that point, and it's called the point of tangency. Makes sense, doesn't it? All right, it's called the point of tangency. That's pretty important. We're going to talk about that point quite a bit today. All right, so that's super important. It's the point of tangency. So there are things that happen with that point that we are going to discuss a little bit later. All right, let's move on. So that's our definitions. Actually, Oh, here's another thing. I don't think we really use this very much. But I don't know, it's kind of weird. But what if we did this? What if we put a point here and I called this F, I called this G. Now, do you see there's a line segment right there, FG?
Yeah.
All right, so like if I went from here to here, okay, that's a line segment. They call that a tangent segment, all right, because it's a segment that's part of the tangent. Does that make sense? So it's not a chord, is it? Because a chord has, right, because it only's got one point on the circle, right? A chord, like this one right here, that yellow one, has 2 points on the circle, okay? This is, again, it's a segment that's part of the tangent. They just call that a tangent segment, all right? I'll just write that there. I don't think we really use that very much. In fact, this is the first book that I ever remember describing the tangent segment, at least the one that I've taught out of. Okay. Yeah, I mean, you might have to know that at some point. I don't know. I haven't done all the homework problems, so I'm not really sure what they ask, but we can call that the tangent segment. Again, like I said, I don't really think we're going to do a whole lot with that. All right, let's do a theorem, though. All right. Let me read it off. I'm not going to write it down because it takes too long to write it down. But it's in the book. I say this almost every day, don't I? It's in the book. You can write it down if you like. You can copy it from the book, but I'm just going to read it to you. Then I'm going to draw you a picture, right, that describes that theorem. So the theorem says, if a line is tangent to a circle, all right, so let's draw a circle. There's a circle. And it says, if a line is tangent to a circle, so let's draw one. In fact, I'm going to draw one. I don't know if I can, that's close. I'll pop it up just a little bit. Okay. That can go anywhere. It doesn't have to go horizontal like this one does, but it could be anywhere on that circle. So would you agree that that's a tangent?
Yeah.
Yeah, so put a line. A tangent technically is a line, so it does technically keep on going in both directions. There's a lot of times we're going to be drawing the tangent where we just draw like from the circle out to another point somewhere, okay? But technically the tangent is a line, all right? But sometimes we just talk about the tangent segment, okay, as we mentioned earlier. But this one, it's technically a line. Now, what does it say? If a line is tangent to a circle, which we have right here, then here's what the theorem says. It's perpendicular to the radius drawn to the point of tangency. That's a lot of words, but I think that makes sense, doesn't it? It's perpendicular to the radius drawn to the point of tangency. All right? So how would I draw that theorem? There's the center. I want to draw a radius. Do I draw a radius there? Is it perpendicular to that one? Is it perpendicular to that radius? Is it perpendicular to that radius? No, it's perpendicular to the radius that's drawn where? To the point of tangency, which would be right there. That makes sense, doesn't it? And look what kind of an angle it makes. Look at that angle right there. I didn't sit there and measure it. I didn't take a protractor out, right, and measure the angle. But what do you think that angle is right there? It's 90 degrees because it's perpendicular. So that radius is perpendicular to the tangent at the point of tangency. Everybody see it? That's not so hard to remember, is it? So if I have a tangent, a line that hits that circle just in one point, if I take that point of tangency and I draw a radius, I draw a line segment to the center of the circle, those are going to be perpendicular. Let's do another one. Let's do a different color. I'm going to click out of it. Sometimes that color doesn't change if I don't click out of it. Let's go blue this time. Change it up. So let's draw a tangent like right there. Let me just so it hits, boom, right there. Okay. Well, thought I made it blue. Why is that not happening? Got to draw it first, and then. So there you go, right there. See that blue one right there? Now watch what happens. If I take the point of tangency, where do you think the point of tangency is? Right there. And if I draw from the point of tangency to the center, that's a radius, isn't it?
Yes.
All right. So what do you think is true about the angle that's made from the radius to the point to the tangent line? That would be perpendicular, be a right angle. Okay, so it doesn't matter how it's slanted. It doesn't matter at all. Okay, it doesn't have to be just horizontal like I drew that one right there. Okay, it could be at some crazy angle, but if I take that point of tangency and I draw it to the center, then I've got a right angle. Easy as that. It's pretty easy, isn't it? Now, you have another theorem. It's called the converse. Do you remember the converse? We always take an if-then, and then we switch it around, right? So this says, let me read it like this. If a line in a circle, okay, in a plane of a circle says, is perpendicular to the radius. So let's take the blue one. If I said that this line right here, this blue line, was perpendicular to the radius, then what must that blue line be? It must be a tangent. Exactly right. Everybody hear me on that? So I didn't say this was a tangent to begin with, but if I take this blue line right here, and it only hits the circle at one point, well, there's the tangent anyway. But so if I take a line and I take a radius, and if they are perpendicular to each other, okay, then this is a tangent. And some people may say, well, what if I did this? All right, that line is still perpendicular to that radius, isn't it? But it hits it in two different places, right? So let me read what the theorem says word for word. It says, if a line in a plane of a circle, okay, that blue one right there, is perpendicular to a radius at a point on the circle. So that's the key right there, okay? So is it perpendicular to a point on the circle right here? No. So I would have to bring it out there, wouldn't I? Now is it perpendicular to a point on the circle? Yes.
Yep.
Then therefore, this line must be a what? Must be a tangent, okay? So it's kind of saying the same thing, except you're switching the if and the then. That's what a converse does. Everybody got it? You got your statement, if then, the converse, you just switch it around, and that's what it's saying. All right? Enough of that. Let's move on. Let's do an example. Remember when I said sometimes we draw these things and the line doesn't necessarily go all the way through? This is going to be one of those things. So let's start here. This is an example. This is example 1. All right, so there's one right there. Now watch what I'm going to do. I'm going to start here where these two intersect each other. Everybody seeing that? Then I'm going to draw another one that's tangent to the circle, like that. Now they're both tangents, even though that kind of stops here. Technically, the line would keep on going, but I just stopped it right there. All right? And then let's do this. Let's find where the center is. It's right there. And then I'm going to draw a couple other ones. Let's do this in a different color. Let's go yellow. Okay, so let's go from here to the point of tangency, and let's go from here to there. Everybody see that? All right, so it went to the point of tangency. What must be true about this angle right here? It's perpendicular. It's a 90-degree angle. That's perpendicular. That's a 90-degree angle. Now they tell you some stuff. They say that this is 3x degrees. They say this one down here is x degrees, and that's it. So here's the question. The question is, find the measure of each angle of this quadrilateral. Now, they do name it, so this is A, B, C, and D. So quadrilateral A, B, C, D. I want to find the measure of every angle in there, all right? So I already know B and D. That's simple. What is that? It's 90, all right? So I got B and D, no big deal. So angle B is 90. I got to find angle A. I got to find angle C. But I know angle D is also 90. So that was simple. No big deal there. It's A and C. So how in the world do I find that? Well, this is 3x. This is 1x. What do I do in this situation to solve for x?
No.
I don't. That's right, because it's a quadrilateral. So what do all four of these angles do in a quadrilateral? They add up to be what? 360.
Like 3x plus x equals 180. Could you do that too?
You could. Yeah, you could. But I want to show you like why you could do that. All right. So let's add all four of them up. So 3x plus x plus, let's just do this in our head. What's 90 and 90? It's 180. Okay. So technically this is what you're doing, but Zion was exactly right that you could just set it equal to 180 because what are you going to do here anyway? You're going to subtract 180, which gives you what? 180. So this is going to be 4x equals 180. Can you do this in your head? Divided by 2. What's 180 divided by 2? What's 180 divided by 2? 180 divided by 2. It's 90. Then divided by 2 again, that'd be 45, right? So 180 divided by 4 is what? 45. Without even using your calculator, right? Is that my answer? Do I circle it? Am I done? No. Well, almost. I got one of my angles is that, isn't it? So angle A is just x, and it's 45 degrees. So we put 45 degrees. And this is 3 times 45. Right, so what's 2 times 45? That's 90. Plus another 45 is 135. Okay? And there you go. That's what they asked for right there. That's pretty easy. Really, you didn't have to know a whole lot about tangents on this, did you? All right, because we haven't really learned a ton about tangents. Really, the only thing that we've learned so far, about tangents is if you have a tangent, it's perpendicular to the radius at the point of tangency, right? That's basically all we've learned so far. So really, the only thing new that we learned on this problem was that that's 90 degrees and that's 90 degrees. Okay? All right, let's do one, though, that, this one's pretty easy, too. I kind of like the circle chapter. The circle chapters, I think, when I teach circles, it's been 10 years since I taught it, but I always remembered in my head, it's one of my favorite chapters, just because, I don't know, it's kind of easier, maybe.
If you keep it like this, I will be so happy.
It won't all be this easy, sorry. Let's make this a little bit smaller. Now, watch this. What if I took a point outside of this circle? Everybody watching? Okay, there's a point outside of the circle. What I'm going to do here is I am going to draw a tangent from the point outside the circle to the circle itself. Everybody see that? So I'm going to draw a tangent. And then, where is it? Right there? Okay. And this is the point of tangency. Oh, that's nice. Didn't realize it did that. Let's do another one. If I draw it from here to there, watch, if I keep that selected, then I draw a little dot. Oh, it didn't do it. Why didn't it do it that time? That's so weird. Let's try that again. Oh, maybe because... Anyway, who cares? I don't know why. Let's... hold on. Let's get rid of that dot right there. I don't know what I'm doing. Let's try this again. Nope, didn't want to do that. There we go. There we go. Let's get rid of that. How can I not get rid of that circle? Anyway, forget that dot right there. Let's just put a dot here. So this is a point of tangency. All right. Here's the deal. You have a theorem that says this, and it's very simple. It says tangent segments. So this would be a tangent segment, wouldn't it?
Yeah.
Because it doesn't keep on going, right? But it does hit the circle at one point here. It hits the circle at one point here. So they are tangent segments. So what I said earlier about us not really talking about tangent segments, I guess that kind of flew out the window. So we do talk about it a little bit. This is a tangent segment. This is a tangent segment. It says tangent segments from an exterior point to a circle. Is this point an exterior point?
Yeah.
How do I know it's exterior? Because it's outside the circle. Very good. What do you think might be true about these two tangent segments? We'll call this x. What do you think is true about ax and bx? They are equal to each other. Exactly right. Okay? They are going to be equal to each other. So this segment and this segment will be equal. So if I told you ax was 5, what would bx be equal to? That would be 5 as well. Simple. Do you agree? Yeah. So far, tangents are pretty simple, aren't they? So far. Yeah, they are. In this lesson, they are. Okay, I think we're going to do more with tangents later. But right now, we're just learning some basics about it. It's pretty simple. Nothing. We're not going to do anything that's hard. It's all easy.
Okay. So you say something's going to be harder.
Look.
I'm not going to be getting this.
Yeah, whether a math problem is harder or not harder is a matter of opinion, isn't it?
Yeah.
Right? It's subjective. You understand what a subjective is?
Yeah.
Yes.
Subjective means you may feel about differently than somebody else feels about it, right? So what I think might be easy, you might think is difficult. What I might think is really hard, you might think, oh, that wasn't so bad. It was pretty easy. So it all depends. All right, so let's do this. Now, it's going to take a little bit to draw this, so bear with me here. Let's just start here. Draw to there, and then I'm going to draw to there. Okay, so there's one,
It looks like an L.
and then watch it. Actually, I should have done this. Let's draw that to there, and let's draw this. You should be drawing this, not sitting there talking. We discuss this all the time about when I'm taking some time to draw something here. So you should be drawing, and I'm going to extend this a little bit. And then let's shorten this one a little bit to there. There we go. That was actually pretty good. Nope, that's not pretty good. I messed it up. I don't want to draw a triangle. Oh, I know what I want to do. Stupid. I'm dumb. Let's do this. Let's do that. Sorry. So let's go to here, and then let's go. I don't know. I knew. Thought I'd be able to do this a lot easier. Hold up. Don't lose me. Guys. So let's see. If I drew that like that, and I drew this. Guys, stop whistling, please. It's in the book. It's example 2. There we go. That's kind of dumb, but it's close enough. It kind of looks like example 2 in the book. If you look at example 2, it kind of looks like this. Kind of. It's not perfect, but all right. Let's enlarge it. I tell you what. Let's not do that. Let's do this. Let's do this. Let's enlarge it. Oops. Let's make it a little bit bigger so we can write on it. Okay, here we go. Now, they give you some stuff. Let's label it. This is P. It's supposed to hit right there. That's a W. This is Q. This is X right here. It's supposed to hit right on the circle, but use your imagination. This is Y. This is S. This is Z. All right. So they tell you some stuff, and then they're going to ask you for some stuff. So here's what they tell you. They tell you that this little segment PZ is 4.2. They tell you this one is 3.1. They tell you that this one is 2.7. They say this is 1.4. This is actually, it was a lot harder to draw this thing than it is to actually do the problem. Doing the problem is actually pretty easy, all right, if you know that last theorem that we just did. So let's take a look. What we're trying to do is find the perimeter of this quadrilateral. All right, see that 1, 2, 3, 4 sides? We want to find the perimeter, all right? So what are we going to have to do? We're going to have to add up all the sides, right? Well, I know this whole side, PS, don't I? 4.2, 3.1, yeah. But what about all the other ones? Like this side right here, RS, I don't know anything on RS. That's right, exactly right. Okay, let's go from point S. If I go from point S, tangent to this circle, tangent to this circle, what's true about those tangent segments? Well, they're not. No. They're not perpendicular. They're perpendicular to the radius drawn to the point of tangency. They're congruent, right? So if this is 3.1, then what's this right here? SY. That's also 3.1. See how easy that is? That's really the only thing about this theorem that we're trying to learn here. So what is RY? 2.7. What is QW? 1.4. And what is PW? 4.2. Now, did we fill everything in? Yep, everything's filled in. So what do we do with all those? Add them all up. And I'll do the work for you. If you add them all up, you get 22.8. And it's in centimeters. I didn't put centimeters on this, but it's in centimeters. So we'll do that. It's pretty simple, isn't it? Yeah, I agree. We got 7 minutes. Okay, so we got time. Let's do this. Let's see, that's all right. I've got that. Let's make this a little bit smaller. About right there. Oops. It's not going to be inside. Well, you are going to have one a little bit in a second. All right. Now watch this. What I'm going to do, now I'm dealing with two circles. I'm sorry. Now I'm dealing with two circles. So what I want to do is I want to draw a line, okay, that is tangent to both of these circles. So how many tangents can I draw that are tangent to both of the circles? All right, let's draw one of them. Okay, so let's say, actually, I'm going to have to start from the circle. You can do 4? Okay. So let's extend it out a little bit. So there's one. Do you agree? Where could we do another one? Maybe from here to here? Like that?
The bottom of that one to the top.
Yeah, you got it. So there's two. There's two tangents, and they're tangent to both circles, right? It hits the circle at one point here, 1 point here. This one hits at 1 point at 1 point. Yeah.
Couldn't you do so?
I'm not done.
Start on the bottom or the top of that circle and you draw like an X.
Yes. So you don't have to start from here, but let's just start from here. So you could draw from here to there, couldn't you? All right. Would you agree that they are tangent as well? Or that line right there is tangent to both of the circles? All right, let's do another one. So you could have another one that kind of goes like this, right? Then I extend that out. So both those pink ones are also tangents. So how many tangents can I draw to both those circles? 4 of them, okay? So the yellow one, listen, I'll keep it in yellow. Oops. The yellow one is called exterior tangents. Why exterior?
Because it's on the outside.
Because they go the outside of the two circles, right? See, the yellow one is outside these two, and this yellow one is outside. So take a wild guess on what do you think the pink ones are going to be called? Interior tangents. So these are called interior tangents. All right, that's just a definition. It's kind of nice to know that. All right. We got 5 minutes. Okay, I got time.
Good morning, teachers and students. Just a few sports dismissals. So track and field, boys varsity, you have a dismissal time of 2:15. You'll be departing the upper school lobby at 2:25. Varsity baseball, you have a dismissal time of 1:50. Varsity softball, you have no early dismissal, you're being dismissed at 3 o'clock. And with the bell rings with the following students who touch the offense: Kyle Manley, Ray Romano, Elijah Borowski.
All right, let's take a look at this. So now we have something else. Let's just keep this white. Look at these two circles. Do they intersect each other?
No.
We wouldn't say they intersect each other. They touch each other where? At one point, tangent to each other. That's right. So, listen, we're almost done. Got a few minutes. We're not finished yet. So we would call these tangent circles. So the circles themselves would be considered tangent to each other. All right. So if you wanted to draw a tangent to both of those circles, where would it be? It would be right there. That's the point of tangency of those two circles. Agreed? So would I draw it like that? Or like that? No, I would draw it what? Kind of like that, I guess. Might have to mess around with it a little bit more. But yeah, that's pretty close. Right? So that would be the tangent between those two circles. Agreed? So those circles themselves would be considered to be tangents. So we would consider these external tangents. I don't have enough time. You write it down. These would be external tangents. I could, let's copy and paste and just make this one a little bit smaller. Watch, I could also do this. Let's put it over here. What about those two circles, this big one and this real little one?
Internal.
They would be called internal tangents because they do what? They are tangent
Inside.
right there, and the circle is inside the other circle, okay? So I could draw another tangent line, couldn't I? And that would be, I don't know where the angle is exactly, but let's kind of mess around with it. That's pretty close. Would you agree? All right, so that would be tangent to both of those circles. So that line would be tangent to these circles. This line would be tangent to these circles. This is internally tangent. This is externally tangent. And that is it. All right, so your homework, if you didn't get your worksheet thing, it's section 8.2. And it's numbers. Now, I wrote it wrong on there. I think I put 7 to 10. I want you to do 6 to 10. And then 25 to 30. And it's pages 355 and 6. 356. Okay? Have those finished for tomorrow. Tomorrow is just going to be a question and answer day over these two lessons. Okay? So try these, though. Don't just say, hey, he's going to go over it in class tomorrow, so I'm not even going to do it tonight. No. Do it tonight so that you have legitimate questions tomorrow that you can ask. Everybody got it? All right. Have a seat till the bell rings, please. Don't stand up.